Hi, in this video, we are going to be starting off with understanding the operating systems overview. Okay, so with the last lecture on the UART serial communications, we have basically completed all the device drivers, okay, that we need to learn. Of course, there are a lot more features and functionalities within the Cortex M0 Plus microcontroller on the Freedom board. Okay, so it's good for you to explore on your own. Okay, but in terms of what I wanted to cover and what is essential for the project. All of that has already been covered. Okay, so now we're going to start off with the operating system. Okay, so in this first lecture, we're going to just have a quick overview on some of the OS components, things like process management, memory, files, I/O, networks, security, GUI, and so on. Okay, so we're just having a quick overview just to understand where this OS is coming from. Okay, so firstly, operating systems, okay, deals with various kind of activities, okay, which we call process. Okay, and what we generally say is every application is sort of abstracted as a process. Okay, and a process can be looked at as an instance of a running program, and you can have multiple processes running the same program at the same time. Okay, so the easy way to relate to this is, for example, in your desktop, okay, you can have multiple instances of a Microsoft Word application or a browser, okay, and they each have their own independent memory space. Okay, so when you open multiple Word documents or PowerPoint presentation slides, each of them have their own memory space, and all of them are sort of communicating with the operating system that you're running on at the same time. Okay, and for each of them, you can have your creation and destruction, like how you activate the application or close the application. And of course, there are other things that we will also be covering in the next few slides, such as scheduling, how processes can communicate with each other, and how they actually maintain this concurrency, okay, or real-time nature of how a OS application is supposed to be like. Okay, now in terms of memory, okay, every application that you run uses memory. Okay, so the memory is both in terms of the actual program as well as the data. Okay, and you need to be able to have some mechanism of managing this memory. How can different processes share a common memory pool? Okay, how can you make a small memory look even bigger, and so on. Okay, so these are some of the objectives of the OS, okay, to organize a processor's memory. Okay, so when you launch a process, how does it uh, make use of the common memory pool? Okay, so again, let's if you look back at our desktop application, when you have so many gigabytes of memory, how does each process get allocated a certain amount of memory? And if it wants more memory, how does it request from the OS, and how does the OS manage all of these? Okay, so these are all responsibilities of the OS in general. Okay, another, of course, important task is managing the files as well as the I/O. Okay, so files are huge chunks of data, and when your system requires files, then the OS generally provides some form of abstraction, okay, for us to handle these files, okay, uh, in terms of how they will be created, how they will be accessed, how they will be deleted, and so on. Okay, so that abstraction is also provided by the OS. And in terms of I/O, those are basically the things that we have been covering in the first few set of lectures, okay, in terms of understanding GPIOs, the UART, okay, and the interrupts and so on. So all these are again managing the external interface of your application. The operating system structure basically consists of many different components interacting with each other. Okay, so it's not so straightforward, and it's actually a challenging software problem. Okay, why? Because firstly, you want to create an architecture that is reliable. Okay, uh, you want something that is backwards compatible. Okay, why? Because you may be uh, transitioning from a non-OS environment to OS environment, and you want to be able to reuse your code as much as you can. Okay, or from an older OS you are migrating to a newer OS, so you also want to make sure that it is compatible, whatever that you've written in the past. You want it to be extensible, okay, because you have created architecture for a particular project or a particular application in mind, and as this application grows, there is and the requirements grows, how much can you extend it. Okay, and portability. Okay, portability means basically if I create this architecture right now, okay, how portable is it later on for future applications, okay, that may be similar or may be different. Okay, how do I create something like that? Okay, so these are all challenging software problems, okay, when we are dealing with an OS based application. Okay, so we're just going to look at a very high level overview of some OS architectures. Do not be concerned if you find the next few slides a bit not so clear or a bit difficult to understand. We are not going into the details of the OS architecture in this course. Okay, we are looking at it from an application perspective, how to create a multi-threaded program. Okay, so this few slides is just to give you an idea of the different type of OS that is available and how they are designed. Of course, if you're interested in learning more into actual OS architectures, there are other higher level modules you can take. Okay, but for now, just take it for information. What is important in terms of this module is the application essence of it. Okay, in terms of creating a multi-threaded program, okay, to fulfill some objective. Okay, so let's look at the first type of OS architecture called the monolithic architecture. This is architecture basically looks at a very simple and very efficient implementation where a single program contains all your kernel code. Okay, so a kernel the basically refers to what we call the heart of the OS. Okay, the heart, okay, of the OS. It contains all the important elements that make an OS actually functional. Okay, so that kernel code is basically the heart of the OS, and everything that you do actually taps onto the kernel, okay, to derive some services from the kernel. Okay, so this traditional OS architecture is a single kernel, everything embedded as a single source, and it makes it very easy to implement and fast, but it's of course less portable and a bit difficult to maintain. And of course, since it is a single kernel, as long as something goes wrong within the kernel, the whole system can crash. Okay, so this is how some OSs are built, like for example Unix and Linux, where you have a single monolithic architecture. Okay, so another thing you will see here on the right hand side of this picture, there's three layers. The hardware layer is basically what we have been doing in terms of understanding the CPU, the memory, the IO, interfacing and so on. And we have built up a whole bunch of device drivers, okay, to communicate with the hardware. Okay, so now we are looking at this section here of the kernel, where you have a kernel which is the OS heart, okay, providing all these services, and how we can write processors that can tap onto these kernel services, okay, to create a multi-threaded program. Okay, and you see another two keywords here, privileged and unprivileged. Okay, so what do these two words mean? When we say you are in privileged mode, basically you have full access to all the hardware and all the resources that the system provides. Okay, and generally the OS will run in the kernel, or the OS kernel will run in the privileged space, because you want to make sure the OS has the ability to do whatever it needs to fulfill the requirements of the system. In unprivileged access means you can make use of the OS, you can tap onto its services, but you do not have direct access to some of the lower level hardware or the resources. Okay, you are given some restrictions, and this is important because, take for example, your handphone, your app is something that you download and is running and making use of your handphone's resources, the CPU, the battery, the power, everything. So you want the app to be able to run to fulfill the requirements of the app, but at the same time, you do not want your app to crash the system by overriding some important aspects of the system or the hardware. Okay, so the app in general, for example, has a limited or unprivileged access, okay, when it's running on its system. Okay, whereas the OS on your handphone will have full access and through a privileged mode. So that gives you an idea of unprivileged and privileged access to the hardware and resources. Okay, the other type of architecture is what we call the microkernel architecture, where the kernel design is a bit simplified, and what you have is these things called servers. Okay, so these servers are the one that tap onto the kernel to provide a subset of services. Okay, and as and when you need more services, you can tap onto the kernel. And the advantage of this is the processes that you create and the multi-threaded processes that you create will tap onto these servers instead of directly onto the kernel. So in that sense, you have this ability to ensure that even if some process tries to mess up or gets messed up and has to be shut down, or the server itself has to be shut down, the kernel will still be able to operate, okay, and still carry on, okay. And even if one server goes down, the other servers may come in to help and take over the role to still fulfill the requirements of the processes, okay. So this is one of the main ideas why you have this microkernel approach. Of course, it doesn't come for free in a sense, because this requires a lot more memory, and there's a lot more context switching, because there's a lot of servers requesting the kernel's resources concurrently, okay. And because the servers are also communicating with each other to fulfill the requirements of all the processes concurrently, there's a lot of inter-process communication, okay. So that is one of the main things about this microkernel approach, and it's not so easy to implement such a OS architecture, okay. So generally, as you can see, monolithic has a better performance because it's very easy and very fast, okay, a single kernel. Whereas microkernels have this idea of modularity and extensibility, okay. So these are the sort of two main comparison points between these two architectures. Again, as I mentioned, this is just for your information only, okay. We're not going to go into any of these details, okay, because our objective of this module is more at a application level, okay. For modern OSs, okay, we generally have a hybrid approach, which is across many OSs in the market at the moment, okay. And this is just to introduce you to some other types of operating systems. Of course, we all know the mobile operating system space, okay. We have the Android, we have the iOS, and previously used to have the Palm OS and so on. So there have been quite a few operating systems, or there are a lot of operating systems for specific purposes, okay. So for networks, for example, they also have their own operating systems, and the main objective is to make it uh, tuned towards the objective of networks, which is a lot of data transfer, file sharing, and streaming, and so on, okay. So when you say an OS, all the general principles on OS still apply, but they may be customized and tuned to offer a greater performance in specific areas, okay. So that is a network operating system. And there's also another type called the distributed operating system, very much similar to the microkernel, okay. So the microkernel plus it has specific service components with each microkernel, and the whole idea is, like I said, that they want to distribute the operations of the OS across multiple nodes, okay, and they all will work together to fulfill the requirements of the system, okay. And the main thing is, as you can see, or as you will see along the way, a lot of things are actually abstracted by the user, okay. So a user may not be fully aware of how things are being done, but at the application level, it will, as long as it is done, okay, then your requirements are fulfilled, okay. So it is a lot more complicated, for example, distributed OS, because of the distribution of work across multiple nodes, okay. So you need to schedule them, and you need to provide some form of parallel processing, okay. So it's a lot more complicated. What we are focusing on for this module is the RTOS, okay, the real-time operating system. And the main idea of the real-time operating system is to meet specific timing constraints, okay. There are two types of timing constraints. We will say generally they are hard real-time constraints or soft real-time constraints, okay. Or sometimes we call it hard real-time systems or soft real-time systems. And the main difference is whether that real-time deadline is very, very critical, or there can be some leeway in it, okay. So for some systems, that real-time deadline is very, very critical, such that if you miss even a single deadline, it could mean a total system failure, okay. Whereas for some systems, which we call soft real-time systems, the deadline is still there, okay. But even if you miss it by a certain amount, it is still acceptable, as long as you complete it within a reasonable amount of time, okay, or at least you finish it, okay. So a soft real-time system has some deadlines, but maybe there is some leeway in the actual timing, okay, as long as you finish it. Okay, so there's a wide range of real-time systems out there. Okay, you talk about robotics, machinery, aircraft control, and so on. Okay, so there's a wide range of industrial applications for a real-time operating system. And what are the key things? Okay, so the most important factor of all is of course this predictability and determinism. Okay, so this predictability is very important. Okay, so take for example, you uh, on your desktop you try to double click on a Microsoft Word or an internet browser. Okay, in some cases it may open up within 1 or 2 seconds. In some cases it may take 4 or 5 seconds to open up. Okay, so that predictability is not there. You know it will open up, you know the application will launch, but you cannot say for sure that it will always launch within 2 seconds. You cannot say that for sure. Okay, so that is where a real-time system comes in. That means I must be able to say that if I click on this button, within 2 seconds this application will be launched and will be ready. Okay, so that predictability and determinism is what a real-time system offers the user. Okay, so the responsiveness and the user control is very important. Okay, so this is another interesting thing. Is real time equals to fastest response? Okay, so many times when you first hear the word real time, you may think that real time is the fastest response. Okay, but it's not the case. It is not the fastest response. It's a response that is fast enough. Okay, so always remember it must be fast enough. Okay, so what do you mean by fast enough? Okay, so if I say that when I press the button, the LED must light up within 2 seconds, that is my deadline. So if I press the button and within 2 seconds the LED lights up, then I am fulfilling the real-time requirements. If my requirement is if I press the button and I give you 20 seconds to light up the LED, then as long as you do it within 20 seconds, that is also real-time. Okay, so it's not to say that it must be in microseconds, nanoseconds, or picoseconds range. It's just about making sure that you have a deadline and you can meet the deadline. Okay, regardless of what else is happening in the system. Okay, that is the main objective of a real-time system. Okay, and of course another important thing for many real-time systems is fail safety. Okay, um, so this is very important because many real-time systems are used in a wide range of critical applications where a failure could mean to a huge disaster or loss of life or a huge catastrophe. So we need to make sure that there is a fail safety. That means if the system is detecting that something is going wrong, things are not uh, uh, going as expected, some voltages are dropping, some motor is not spinning correctly or something like that, it must be able to detect that there is some failure in the system and must be able to progressively shut down the system to a level of safety. Okay, so that is important. Okay, and that is also another key requirement of RTOS systems. Okay, and of course to fulfill all of this you have a very advanced scheduling. Okay, because there's so much of context switching and interrupts and everything that's happening concurrently, and you also need to make sure you manage the memory allocation of the various requirements of the processors or threads, okay, effectively. Okay, okay, now another common term you will see sometimes is this thing called embedded operating systems. Though in general RTOS and ERs are not exactly the same, in general we can say that embedded operating systems also have timing constraints, okay, which need to be met. So this embedded operating systems term and RTOS are generally used interchangeably, okay, but in general we are saying it this way, that most embedded systems do have timing constraints, so we can classify them as RTOS based systems. Okay, so again comes down to the same things: predictability and determinism, that real time nature must be fast enough, and of course some aspects of the system may not be so important. Okay, so for example I may have to press a button and activate some motor, okay, and at the same time update the LCD. Okay, and as long as the motor starts to turn, that is the critical part. That real-time response to the motor is important, but maybe updating the LCD, if there's a bit of delay after that, that is fine. Okay, so when you say a system is real-time, not every requirement may be a real-time requirement. Okay, so some requirements that are very critical to the system's safety and performance, those have to be real time. But other things that are more for nice to have kind of thing, like the GUI and so on, maybe they can have some soft real time requirements. Okay. Okay. So again, if you look back at some of our earlier tutorials, okay, we looked at this idea of the super loop. Okay, so super loop is basically the concept of you having a main loop. Okay, and with the main loop you have something that is always running, indefinite loop. And what you do is you have interrupts. Okay, so you can have a push button interrupt, you can have a serial interrupt, and so on. And we saw that the whole challenge with this approach is that predictability is not there. Okay, because you do not know when the interrupts will happen, and whenever interrupts happen, your main loop gets extended, so things become very very difficult to predict. Okay, and of course sometimes you may also need to synchronize between one ISR and another ISR in terms of the data, or the flags and so on. So it's a lot more challenging. Okay, and anytime I change the ISR or the main loop, okay, the effect is again has to be re-examined, right? Because if suddenly my ISR gets longer, my main loop gets longer, or the period of my interrupt gets shorter, so as long as anything changes, then the whole dynamics of the whole system changes. Okay, so that is a huge drawback for the approach that we have been used to, where we have this while loop and interrupts. Okay, though it has served us well, it has its own set of issues, right? And of course, with RTOS, with us moving towards RTOS, what we are doing is we are moving all our objectives to be encapsulated into tasks. Okay, and then we are going to schedule them. Okay, and what you will see, okay, over the next few set of slides, okay, as you understand how a multi-threaded environment works, is you are able to create a system with much better program flow and event response. Okay, you are fulfilling multitasking. Your ISR can be a lot shorter and more deterministic, because you can be very sure of what you're going to do and make sure that the uh, threads will later carry on with the next follow-up steps. You are able to have a lot more better communication between tasks, and your resources are also very much well managed, okay, once you go towards the RTOS environment. Okay, so for this course, there is actually the Keel RTOS, so Keel RTX, okay, which is already integrated into our Keel IDE. Okay, so you in the next lab exercise, you will actually be creating your first multi-threaded project. Okay, so I'll be guiding you through that process and explaining to you how it works. Okay, there's of course another API, the CMSIS RTOS API. Okay, so this is again another way of writing your RTOS code. Okay, but we will stick with the Keel RTX, okay, for this course, so that you actually understand all the low level uh, kernel calls that we are making. Okay, so that you have a very deep understanding of what the OS is actually doing, or how the OS is actually behaving when we are making all these kernel calls. Okay, so that wraps up the overview for this OS introduction. Now in the next video, we will be discussing processes, okay, to better understand what are the different states of a process and how they will be able to transition as they execute, okay, in a multi-threaded environment. Okay, so thank you. Look forward to the next video. Thank you.